talk this morning. So it gives me special pleasure to welcome my distinguished colleague from the STAR collaboration, Professor Sergei Voloshin from Wayne State University. Of course, I know Sergei from early days of STAR, and he and our post-cancer really were the pioneers of people in the STAR collaboration that pushed the event by event, the elliptical flow analysis. And of course, that the flow analysis has been one of the most successful program in heavy ion physics. And then also in terms of searching for chiral magnetic effect, and Sergei is also one of the early pioneers in that experimental searches. And of course, these days we are still using one of the correlators that Sergei proposed. So I think his impact, his influence in this field, I think it's a very, very experimental overview on chirality and polarization. Let's welcome Sergei for this special seminar. So Sergei, take over.
Okay. Yeah, thank you very much, Juan, for very nice introduction and me. And okay, nice words. Thanks. So today I was just asked just to give an experimental overview on this chirality and polarization. Those two topics, they have quite a lot of common probably thinking theory, and from the experimental point of view, it's not that much. Also, there is definitely an overlap, and also in physics and even in techniques of what we are looking. But this overview would be almost as the two separate parts. And I'll try also just not to spend too much time on each of them. Each of them, if we go into detail, would take well over an hour just to describe not only technique, but the details of the measurement and different consequences of how they correlated between themselves. And so I will start with chirality. And again, it's not a comprehensive overview, it's not a review of everything in there. I'll try only just to make some logical path of what's happening and what we are trying, emphasizing probably on assumption and what we should be careful with the assumption sometimes. Even new approaches, I will be very brief and very little relevant on those. Similar on the polarization, also here I will be probably show more existing results, because the results, first of all, a little bit not that many, but those are very important, and let me give some comments. And so in both cases, I will provide a little bit of history, because it appeared that both, at least like a new era in this parity violation study and in polarization, although both of those existed before 2004, but they kind of started in 2004. And one is by proposing edema with Chiral Magnetic Effect, and another a global polarization, which I'll just mention later. And it is even interesting that this is a slide from my STAR collaboration talk about this effect for Chiral Magnetic Effect. But even the cartoon in here, it has this orbital momentum pointing, and that shows that it is at the same time, it was a discussion of the global polarization as that is started. We did have at the very beginning, so there is a lot of progress during those years, both in theory and in experiment. On the other hand, we still don't have a very precise neither theoretical predictions, nor we can point down if there is such effect in the experiment. And I will describe a little bit more on what is shown, but you will see a very similar results from later on, that some correlator, which I'll explain, for the same charge particles, they have some noticeable, say, negative value. For opposite charge particle is more or less the same. This correlator, it was given a name of this gamma correlator. It's not me who gave it, but I will just use because it's a common. And so let me just, again, for those who are not very familiar with the subject, mention, first of all, yeah, we will have in a week the theoretical talk on all those subjects, and I'm looking forward for that. And so very briefly, just what this chiral magnetic effect is just that we start with the chirality imbalance in the system, which is really most of the interest because that's where the parity is violated. And then we know that there is a huge magnetic field because those positively charged nuclei moving in opposite direction with some impact parameter, they create magnetic field. Then it happens anomalous transport, and that's what is written over here. And so there is an electric current along the magnetic field, which leads to this kind of a dipole moment of the system, which is manifesting of the parity violations, a chiral magnetic effect. And so what is happening in here is that if you look more carefully, that the positive particles would be moving in the same direction, but oppositely charged particles are negatively down. And that's the correlator, really what wanted how to measure. And so it just measures the correlations along the magnetic field and with opposite sign perpendicular to the magnetic field. And why is this difference? Because you can subtract or suppress all correlations which are not related to this angle. And in this case, you subtract, and your background is still proportional to V2, but it is suppressed by V2, so it's more than probably 10 times. It started in 2004, but it took a few years before it went public. And then it was a poster at Jaipur, and later in Cork Meta, that's where the first results were presented on those measurements. And it's just published. Why I mentioned, because some of the background which I will discuss, it was started already and discussed quite in details in those papers. And so what kind of the background you should expect? First of all, I did mention that this correlator which we measure, it measures this projections on the reaction plane with this cosine between two particles and subtract its projection perpendicular to reaction plane. And so there is this background, whatever it is, it could be not CME in plane and out of plane. The difference between them should be proportional to V2, and it was pointed from the very beginning as that it still exists, and it could be, as I say, it is suppressed by a little bit more probably than 10 times, but if it's not enough, it's not enough. And it went under the name the flowing clusters. This is from Quark Meta talk and Star, which presented, and at that point it was already clear that the correlator, for example, all those points are some estimates in some models, which you could just read. So it's not expected that the correlator would be zero, but due to this flowing cluster. But it did not explain that big difference between same charge correlators and opposite charge. We also thought at the same time, but we can probably think again, that the global polarization, which I will discuss later, it also leads to the correlations, charge-dependent correlations different in plane and out of plane. But at the same time, again, it was measured by star, found that it is very small, unlike it was a prediction like almost 30%. While we don't have any model which would describe the experimental data, we do have an idea, and it came from Scott Pratt, that goes under the name this local charge conservation, that flowing clusters could be many more in some sense, or much stronger than we think they are. And so they could contribute, and that's, we have just to somehow find out how to suppress it. I mentioned that this is physics, so it cannot be suppressed, so it's just correlations which we measure in plane and out of plane are different for some other reasons than CME. There is another important thing to have in mind, and this is measurement. The correlator is done, so it's over here, it's reaction plane, but we don't know the reaction plane. We can only reconstruct it somehow, usually from other particles. And this equation is phi c, some c particle, and we hope that it follows the reaction plane. But in principle, it can be totally different, and it can be, say, dominated by some other process, like, something like, for example, back-to-back jets, and I have particle A and B here and C over there. And then the correlator, which I would measure, so it's a charged particle, the correlator, which I would measure, would have nothing to do with the reaction plane. What I want to point out that in this even quark matter, all the shaded area, you see it's a huge shaded area, it's all estimate of this background. And that's why we wasn't sure about anything, say, over here. It's only mostly over there we knew that what we measure is what we wanted to measure. And it's just important to have. And that is emphasized in those two is also figures from PRL and PRC. And you see here those backgrounds shown by those thick lines over here. And this is for copper and dashed thick lines. And you can see that the estimate from RHIC, they go just over the point. So it's entire, this is entire background. That was our estimate. And that is written over here, thick lines is the reaction plane independent. So it depends on the measurement. And before going to some discussions of some newer measurement, I should also mention, and that's also important, measurement was from which was done by Alice. And in this point, you see that you see both data from RHIC and from the Alice. It is surprisingly close. It's still surprisingly close to me. I mean, it's already 7 years after the measurement. And why it is surprisingly close? Because what Star measured, that the signal depends on acceptance, on delta eta window. There is a difference in acceptance. It's not seen, even 20% difference here. Then, if it would be CME, the effects change because the magnetic field lifetime and magnetic field in LHC and RHIC should be different. As the results are quite similar. It's interesting if it would be background, or in fact also in CME, the effect of almost 3 times higher multiplicity density is again not seen. So results, at least for me, is still this very close measurement at 2 different energies, still a little bit surprising to me. But that's where we kind of started. The program really started much earlier. And so we wanted, I don't know what is here, let me just remove it. So like a program to measure the CME signal. And so the goal everywhere, at least for me since that time, was to identify the presence or lack of CME at the level of about 5% of the measurement which I just showed from STAR. And so from theory, we do have some guidance, but it's not any quantitative statement. And anything really what we have at hand in our disposal, as remember that your background depends on anisotropic flow on this B1 minus B2 proportional to V2. And so we have somehow tried just to manipulate or define the different system and observable, trying to separate the two at the level, again, at least for my point, not just to do some measurement, but to measure something quantitatively. And so what I identify, I just have a list of different approaches. It's probably not full, but quite comprehensive list. And I have my personal view on those approaches. With the green is just that what I expect, some signal and meaningful results. With red, it's not that meaningful. And in I just cannot talk about everything. I will give only some small comment of what is shown in here in dark color, and I wouldn't comment much about the green. But if you have questions, I can always just ask questions, and we will have this discussion. And so I will start with just making comment on some particular measurement. I'll start with event shape engineering, and just for those who don't know what it is, it's just some technique to select events with larger or smaller flow within the same centrality range, for collisions of the same centrality. And in terms of the application to CME, it was written even also in the original paper on that it can be used for CME search. So if you change your flow, you change your background, and that's the idea. That's how you can select. And there are some special prescriptions how you can do it. It's not that important. And in principle, you could just estimate, and that was also supported by later measurement, that you can vary flow or V2 value by a factor of 2. But if you want good statistic, it's probably 1.5. That's factor 1.5 with the good statistics. But there are indeed, you have just to be careful over here, and just also to mention that it's not always happen. And I think that, for example, Star published a similar results on selecting different events. And what is shown in here is something related to this V2. Also, it's called V2 observed. I don't think it is a good real idea just to call it this way. And you don't expect V2 to be negative if it's measured with respect to the participant plane. But anyway, so V2 would be increasing in this direction. And there is some quantity which is probably sensitive to CME, not probably, but at some point. But what was done that these particles which we used for event selections and for the measurement were just the same or used from the same window. And then you're completely dominated by statistical fluctuations. And also there is probably some information in here, but from my point of view, such approach doesn't do much, doesn't bring much, because it's very difficult, if possible at all, to interpret. Somewhat better and really quite close. And in fact, this event shape engineering trick is quite difficult due to the multiplicity, because you do have to use some particle to select events. At LHC, the multiplicity is much higher, and CMS, the coverage also, the pseudo rapidity coverage is large. So it's much more straightforward to do this analysis. And this is from their paper. And so they do put that it is about 7% in lead. I will comment about PLED later. So it's about 7% which is just the accuracy which I was hoping. But there is something not correct, and namely, this assumptions over here, and they assume that V2 is independent of multiple, the signal is independent of V2, and this is really not correct. And so that's my conclusion, is that really 7% is not correct number, but it's probably close to correct. Then with Alice, that's the analysis from Alice, and just to show that the signal would depend on V2, I just presented this this slide which showing its model calculations, but why your CME would signal on V2, would depend on V2, is because your measure all with respect to reaction plane or event plane, and that event plane correlations with the impact parameter, which defines the direction of the magnetic field, would be weaker and V2 is smaller. And that has to be to take into account. If you take this into account, Alice, and that's, I think, that's how event shape engineering should be done, the Alice measurement, and that the signal is still small, so it's dominated by, but it is probably about 15% or so, might be up to 15% or so. And so then I just mentioned that I would just comment about this PLAD a little bit later. And this is just two quite similar measurement. One is from CMS. And so the idea is just using we go to the small system, the correlation between flow planes and magnetic field, if any is there, would be totally random. And so you wouldn't expect CME. And a similar measurement is a slightly different representation, so it's multiplied by the charge here, is published by Star. And so the question, so the idea was, you see, these points are similar to those points, and that's kind of all the background. And similar over here, also, if you look carefully, it's probably P-LED slope is different from LED-LED. But you remember I just mentioned about this reaction plane independent background, so which depends on the measurement. It's again that what I was drawing this like a back-to-back jets, this background. And while I don't know for sure, also I think it is significant in CMS measurement, but I don't know the level, but in STAR, it is known because the STAR also, the authors did run RHIC, similar to what was done over here. They run RHIC, and over there, it's explained quantitatively, 100%. And so then my real saying is that this reaction plane independent background, it just contributes like this. And it has little to do with measurement in gold. It is a pity really that the STAR did not include the measurement which they did RHIC in this paper. Then I have another comment, because it's also a very popular directions about I called it first double harmonic and the mixed harmonic. It's about the correlation. So you take this correlator, like gamma correlator, but you can change your harmonics. In this case, it's double, and I just showed in terms of my those arrows of subtraction, different correlations, that it's subtracted sides, that there is no CME. And one of the measurements was also presented by Alice. And so this is double harmonics with large arrow bars. It was much smaller than expected. And in principle, you could conclude that it is showing that the CME signal is large. But what I want to emphasize that really it does require detailed knowledge of background, namely to relate measurement with mixed background and not mixed background. And I'll just show it's also here, and it also, I don't have much time to comment on a different, similar approach, really, or at least that's how this CMS measurement was based. So they made some, I don't know, approximation also, I cannot call it approximation, it's just wrong. That some splitting one correlator into two, and namely, for example, in here, that this gamma, general gamma, would be proportional to so-called delta, which is just the charge-dependent correlation between two particles, and V2. But if you look carefully, it's not equal. And even more, for higher harmonics, it could be all different. And again, just because I wanted also to add, I think my conclusion that at the very least, it's not suitable for quantitative measurement. And we can come back to that, but I think this measurement is just not correct. And that was really shown by Prithvi Shribadi at one of the meetings. He just calculated two correlators, which according to this approach has to be the same, but you can see that they are quite different numerically. And that's the idea. So you should be careful with the mixed harmonics. And again, for me, you have to know background. But if you know background, then probably it's not worth of measuring this stuff. Then I have, let me just check. I have already almost half an hour. So I have to mention another approach is, in fact, similar in nature. So you can measure, and this is a measurement with respect to invariant mass of the pair. It is a valid measurement that could be interesting probably later to do, but right now, because we don't know what is the, say, right now, only the estimate for CME effect was obtained after very strong assumption, which I don't think either of them can be true. But the main thing what I want to say is that in order to be quantitative, your assumption should be very reliable. Otherwise, you are not in the game for this, what I wanted, 5% accuracy of the measurement. And this is, from my point of view, again, is not correct measurement. Another thing which I do want to mention about CME is the measurement with respect to so-called flow plane, which is determined by participant plane, and with respect to the plane determined by, for example, spectators, which would be, or at least would be strongly correlated with the direction of the magnetic field. This difference is seen very clearly that if you measure with, for example, flow with respect to different planes. And so this is shown the flow with respect to spectator plane. And you can see that's about 15–20% larger, the flow, if you would measure to the participant plane. That's again. And you remember our background is proportional to flow, while the signal is proportional to magnetic field. And you can play in it. How you can play? I think the best is just to start, which is basically assumption-free, with what I call background scenario. And namely, what you do, you just calculate some quantity, which would be something like gamma correlated divided by V2, but it's made in such a way that you don't need even to know the resolution of this plane. And you can do it with the different planes. And if the flow is the same, not the same. If your measurement, say if the physics contains only background, there is no CME, this ratio should be unity. And again, if you have questions, we can discuss more. And it was, here it is just playing with some Monte Carlo, but for example, it was also reported by STAR for 27 GeV, it's very close to unity. So it is probably dominated by background, but it was measured also in gold, and those estimates were obtained in such a way. And I think the precision in principle could be even increased. And this is one of the methods which I think is fulfills this requirement of 5% quantitative estimate of the signal. Similarly, it can be used in isobar because it just calculates this ratio of isobar, and this double ratio is almost assumption free. It would be insensitive to small difference in flow in both systems if it exists. And in terms of the interpretation, if you see that this ratio would be different for two different isobars, you can assume about how it depends, your signal depends on the magnetic field. If it's proportional to the square of the magnetic field, you just substitute the charges over here, and you can get this ME. Again, as many of you know, it's probably a couple or 3 months more in terms of the data production, and we will soon know those results. For the chiral magnetic wave, I have just to be very brief in here. And so you remember what it is. It's just some signal which would create, say, positive or negative charges either on the equator, on the poles, and that would lead to the dependence of, in this case, of V2 on some vector charge present in the system. So this is a vector chemical potential, and it would lead to a particular current which you could just measure. But I have just probably to go faster over here. The only thing I will just very briefly just mention that in ALICE it was proposed also a correlator which can be measure all the things differentially, and this is so-called three-particle correlator. It was also done for different harmonics, and so again you would expect the signal in one of them in the second harmonic, and you do not expect in the third harmonic. But the problem is almost the same as whatever I said about the mixed harmonics. So it is very difficult to interpretation because you have to know your background quite well. This can be done, in fact, but this study, and that's what I was showing, so that's how it contributes. So the same background would contribute to both CME and Chiral Magnetic Wave, and you can correlate and play on that just to understand what is the signal. But I have just to move and at least have some time for polarization. And so that's where I kind of made this short summary. So our goal is just to get it, and I think at least some of the measurement can go as precise as we need. And we are just waiting for this isobar results. And there are some questions to the theory also. But let me just go to the polarizations. And again, I start with some, so as I mentioned, there is a prehistory, and so this polarization was started even before, but in this 2004, the same year, which I started discussing this Chiral Magnetic Effect. Xinyan published and Zhou Liang published a paper about the global polarization. I also, because I was thinking about those measurements before, I just added a little bit. And in principle, we saw that this polarization, so they estimate the polarization could be very high along the orbital momentum. And in my paper, I will discuss that, for example, polarization of vector meson could lead to the V2. And so I was wondering what is the contribution to V2 and some other things. But in 2007, it was the first measurement by STAR. It was also established how it's measured and found that polarization is really small, but we waited for a few more years before it was measured quantitatively. A really very important paper and very important direction, a really series of papers. There are several papers, and it started with Beccatini, Francesca Beccatini and co-authors, which was showing that it could be obtained those estimates on the polarization from assuming some thermal equilibrium. And he did it only for spin 1/2 particle over here. But if you look more and you think more about this stuff, it's obvious that in some, if you have a thermal equilibrium, those, say, spin degrees of freedom should be also in some equilibrium. And you expect for any particles with any spin. And in a non-relativistic mechanics, it is not difficult really to derive how it should be. You can go also this direction, but then generalized for any spin. And once it was derived, and this is what describes, this Boltzmann factor describes the distribution, you find out that many things were known before, as usual. And I have also some really very short derivations in non-relativistic ideal gas of particles with spin, if you call it non-relativistic. We will see later that at least theory, and that's what I want from the next seminar, about this contribution from the temperature gradient and acceleration. For me, it's still not totally clear how it would behave in non-relativistic limit. Then those as a measurement, like most of it, as a global polarization and how it depends on collision energy and theoretical predictions. There are at least two of them shown over here. They quite describe it quite well. I have also shown some measurement at LHC, which is with larger error bars. Real error bars doesn't allow to show if it is consistent with the predictions, but it's about a few times smaller than at highest RHIC energy. And so I mentioned over here that you can try just to empirically predict what is there, and that's based on some directed flow measurement. Again, I don't have time to explain it really well, but the idea is just if you measure your directed flow, it has different components, and which I would call, at least that's, it is an oversimplification, but nevertheless, you could think about some component coming from the tilted source and so-called dipole flow. And dipole flow, this is probably first who was, this is due to the density gradient. Probably the first who was, at least to me, I think he was the first, is Uli Heinz and Peter Kolb, that was a calculations of directed flow due to the density gradient, which existed at larger rapidity. What is the difference between them is that tilted source would live to V1, but also the so-called mean px would be different because particles just fly at some angle, with dipole flow, which is only due to the density gradient, mean px would be 0. And that's indeed what was measured. But you can use those two to separate the two, and then you can say that only tilted sources contributes to vorticity. You would end up that the polarization should be about 6 times smaller at LHC energies compared to the RHIC, which is consistent with the results like over here. And this is, by the way, this is just how this dV1 d eta goes with centrality. It's describes quite well. I should mention at least one thing which is just common for both topics which I discussed, and namely the magnetic field. And why? Because it would contribute to the so-called global polarization, because the polarization which we measure is perpendicular to the reaction plane, and the direction of the magnetic field coincides with the direction of the angular momentum. And so in principle, if the magnetic field is large, you would expect some splitting between the polarization measurement of particle and antiparticle, because magnetic moment are different for those, which was a hint in the first, say, measurement. But whatever it is, even if it is just in opposite direction, you can make a upper limit on the magnetic field, assuming that, yeah, it exists at the time when the polarization is really produced. And so taking all those measurements, you can put it upper limits on the magnetic field, again, assuming that it exists that long. And what I want to say is that also its own upper limits, it's still quite meaningful, because we don't know the magnetic field at large time to many orders of magnitude. And this is the limit which already put some constraint on the theory, or in this case, on the value of the probably conductivity, say, on which the time evolution of the magnetic field depends. And there are many measurement more differential. I'll show only just a few, and there are some predictions for differential measurement. In here, it's probably you would find, for example, if you take this measurement, so this measurement on pseudo-rapidity, global polarization, it would probably contradict very strong, very peak dependence predictions. This is from AMPT, I believe, because they usually use AMPT. Contradict some measurement, but in general, so we accumulate statistics, we have more and more measurements coming, as well also at different energies. I will mention some of them. An important development, recent development, is related to this slide. And initially, what I wanted to show is that when we measure the, for example, lambda polarization, because lambda, more than 60% of lambda are coming from feed down, we have to estimate this effect. This effect was estimated by several papers. The results are always similar. It's about 15–20% decrease in polarization due to the feed down. But what is done in those calculations, so you have to assume, for example, how your sigma is polarized, and then if sigma is polarized, when here psi is polarized, you have to say how lambda from those psi decay is polarized, and that's what is usually called polarization transfer. That was for the feed down, but it also suggests that the polarization of the Doppler particles can be used to measure the polarization of its parent. And this is a very important, I think, recent development, which I want to mention. And so how the polarization is measured in general, which I didn't mention so far for the hyperons, is via the parity-violating weak decays, via this asymmetry, which is determined by the resonance so-called alpha parameter. And this alpha parameter is so it's, I thought it is somewhere, yeah, no, it's decay parameter here. This is alpha. This is alpha. Say, if you go to Xi, it's already like a 2 times smaller than in magnitude than lambda. And so it's 2 times more difficult to measure. And you have in mind the statistic is also smaller for Xi. But if you would go to the omega, you would see that this alpha parameter is extremely small, so less than 2%. And it's no way you can measure omega polarization in this way. On the other hand, as the daughter polarization from such decay, it would be determined by this polarization transfer, and in this case, by a specific gamma parameter gamma. And so you can measure, it just happened, you can measure this omega polarization by measuring the polarization of lambda. And yeah, for omega, you have to assume even what it is, because you know that it is in magnitude close to unity, but you don't know the sign. And in fact, you can even have a possibility to determine the sign if you assume the global polarization and measure this polarization quite accurately. And so that was done by star. And so what is shown in this plot, this is really, it's 2 results even for sigma. So it's via dot lambda in 2 different ways, just independent. For omega, as I said, it's only one is possible. And this is the result for omega at highest energy, assuming that the gamma parameter is +1. If it would be -1, it would be somewhere over here, but it's still with large error bars. But anyway, that's why I say that it slightly favors this measurement, which was not measurement, it's interesting measurement by itself. And you can, in principle, average those two to get what would be the Xi polarization and check if this idea of the global, because it's global, it means it's not only one direction, but also for different particles. And by the way, it's also measured at lower energy already for Xi, which is also indicated over here. Then I want to mention one thing about one measurement which might relate both subjects. So we still don't know. But you remember I very briefly just showed a slide related to Chiral magnetic wave. The first step of this Chiral magnetic wave was that depending on the vector chemical potential, you have a separation. So you have a J5 current, which would be related or can be related to the polarization. Also, it's not that straightforward. You have to count, charges and other stuff, but in principle. And so it just means that you can measure the polarization and say something about chiral separation effect. That's what it's called. And here I again draw the attention to 2 measurements of star. One is published, one is too large error bars. It didn't go to the paper. It's dependent on this polarization measurement for lambda and lambda, dependent on the net charge of the event. And there are some explanations to that, but I think it still deserves more attention to this one. And finally, I just mentioned, so I have about probably 5 minutes, just to have time also for questions, about so-called local polarization. Yeah, okay, it's probably in my extra slides about some purely predictions for different effects for the so-called local polarization. But the idea is very simple. If you do have your vector field, your velocity fields, they are not uniform, then you might have, you calculate your curl. It would depend on the position in your system, and you can probably try just to measure those effects. And one of the strongest, which we think as of today, of this local polarization, it would be due to the elliptic flow. And this is naively also, it's more complicated. There are some different contributions to this, but naively how it's shown, if your velocity field is like this, you would have a positive contribution here, negative, positive, negative. I should say that, and many of you know that it is in contradiction in terms of the sign and magnitude, in fact, also to the real hydrodynamic calculations, which do include those temperature gradient contribution, acceleration. And I think it's very interesting to understand what is common, what is not common. But the results, you know, that the rod measurement, or at least many of you know, and it it is consistent qualitatively with this picture. But what is interesting, that's how your polarization changes with angle, so it's going in this direction. But what is interesting that, for example, yeah, in here, and that was discussed a lot, but nevertheless, I want just to emphasize, and this is from star measurement of this polarization along the z direction. And so what is shown in here by blast wave calculations, and especially on this one, which goes over the points. You can take this equation, take the blast wave parameters published by Star in 2005. You don't do anything else. Calculate this quantity. It's very interesting coincidence or whatever it is, but it goes over the point. Hydro or MPT, besides it has a different sign. It's also about 5 times larger in magnitude. So the prediction is very different. And so it's would be very interesting to understand. I know that many people are working on that. I want just an advertise. So it was also measured in ALICE. In this initial stages, I hope it will be shown. Yeah, we're waiting for confirmation. But you still can't make a predictions if you want. If you don't know the results and you can make a predictions, please make. And the last couple minutes, just one comment about the spin alignment, because it's also discussed. And was measured really, both by ALICE and Star. ALICE published already these results. And it also what is coming as, for example, J-psi polarization measurement. But I will just mention only about the vector mesons, which they K into scalar, so it's K star and phi. And just to remind you that at least in the approximation, which we are always working, removing all these off-diagonal elements or not taking care about non-diagonal elements of the matrix element, what we are sensitive is only to some polarization either so everything what we measure is the probability for spin of the particle to for the projection of the spin on the quantization axis to be 0, which is like rho 0, 0 in usually discussed in the measurement, which without any polarization effect should be 1/3. This is a measurement from ALICE and also preliminary measurement from STAR. There are some contradictions, but my point is that the effect is huge over here. The measurement is difficult, and that's what I would just comment again here. But the effect, and so if it is, it's probably not the effect which I was talking about this global polarization. Because, for example, this ρ0 measurement of 0.15 would translate to the probability of particle to be polarized of 80%. I don't think, and we expect probably per mils from statistical summarization measurement. I would mention that the measurement I did is very difficult because it directly depends on acceptance, which is not the case for lambda polarization. What kind of acceptance it depends? It depends on probability, how well you can reconstruct your decay of the particle, which is the case, for example, kind of perpendicular in the rest frame of your resonance, perpendicular to the momentum of the particle or along the particle. Those two are very different topology to reconstruct, say, in TPC, and this results heavily depends on your Monte Carlo knowledge of your detector. But that's my hour is off. And so I think the polarization measurements, which we already have, already contributed a lot into our understanding of this dynamics and hadronization. And not that, but it will contribute also to hadron spin structure as well. I just showed that there are some Xi polarization even at 27, and remind you that this 27 GeV data set was, it is a very high statistics. We should expect also precise measurement for lambda and anti-lambda that would put a limit on the magnetic field. We expect more measurement in future, both at RHIC and LHC. And so I will stop here. Yeah, thank you. Okay, and then